Hello and welcome. This is SFU Math 232. My name's Brenda Davison. We are now on to section 1.1, Vectors and Matrices and Space. So what we did is we actually did all of chapter 2, 2.1, 2.2, and 2.3 first. And in that, what we did is we used the idea that you had already of a system of linear equations, and we saw how to capture that that problem that we wish to solve, the solution to a system of linear equations, into an augmented matrix, and then how to use Gaussian elimination to determine the solution. We importantly saw that there was three possibilities: no solution, one solution, or an infinite supply of solutions. We didn't really, we used the term matrix without totally defining it. We used the term vector. We weren't totally specific about that. So what we're going to do now is we're going to go back a little bit and we're going to really be clear about our vocabulary. We're going to introduce some more vocabulary so that we can speak of these things, and we will see that the vectors and matrices, they come up in other things besides systems of linear equations, and we're going to get a more abstract look at them. So a lot of this lecture is about vocabulary, which I think is extremely important. So when we're speaking to one another, particularly in mathematics, we want to be as clear as possible. So when I say a word, you get the same feeling, the same sensation, whatever, the same thought in your head as the one that I intended to convey. So I will try to be as precise as possible with my language, and I want you to do that as well. So if you reading the textbook or you're reading the lecture notes or something is happening and you think, gee, I'm really not totally sure what that word means, it's always a good time to stop. You should every time stop and look it up, even if you have to do it a few times, and then you get the words in your head. And sometimes that's enough actually to get you the understanding that you need to solve the problems. Okay, so we're going to start with the word scalar and vector. So a scalar is an object that can be described entirely by a number. Okay, I'm just going to give a few examples of this. So here's some examples. I would say this: I weigh 60 kilograms. Okay, so that's my weight, and you see that there is a number there associated with that 60 kilograms, and that is simply a number, and it tells you everything that you need. Okay, like this: I am 54 years old. Okay, another number, and we don't need to know anything else. How about this here? I can run at 10 kilometers per hour. Okay, I give you an idea of the speed. And then when you want a comparison, an Olympic athlete can run at 20 kilometers per hour. Okay, so but the point is we have a number, and that number completely describes the situation. Okay, that is what we call a scalar. It doesn't have any direction associated with it. In contrast to that, a vector is an object that can be described by a number, which we're now going to call the magnitude, the size, and as well a direction. So here's a vector quantity. I am traveling east at 10 kilometers per hour. Okay, so in this case, this thing here is a vector. It has a magnitude and a direction. So, and that's what we call velocity, in fact. So we have the idea that velocity is equal to speed. That is the magnitude of the velocity plus the direction. Okay. All right. So here, well, what else? Let's see. Gravity exerts a force of 600 newtons on my body directed towards the center of the Earth. Okay, so we have the magnitude of the force, and then we also have the direction of the force. So that would be a vector quantity. Okay, so we're going to differentiate between those, and we will use notation to do that. And in the textbook, the italicized non-bold things like that, those refer to scalar quantities, and then the bold-faced ones like this refer to vector quantities. Now, you can see the problem, I hope. So this is in our text. The problem is, how do I print in bold? You can't really tell. I mean, I can't sort of print light and then dark and then have it actually be distinguishable. So there's other notations I will use like this, A, and when I do that and I don't otherwise say, that will be a scalar. And then when I want to indicate it's a vector, I will go like that. That is a sort of half, maybe a little bit neater, a half arrow over the top like that. That is going to be a vector. So my notation for a vector will look like that, and you will sometimes see that in the text as well, but that is the equivalent to this, where this is the bold A, right? That is bold, okay, because it's not possible for me to write like that. So that is going to be our notation. We'll have two notations for a vector and a single notation for a scalar. Okay, so here you get the idea. We have here vector v, and this is the direct, we would say this vector v is the directed line segment between A and B, and I would write vector v like that. Okay, so a vector is a line like this. Let's just have a point here where it starts, A, and some point here where it ends, B. So it's the directed line segment between A and B. The A, where the point where the vector starts, this is called the initial point. And this point here, B, where the vector ends, that is called the terminal point. Okay. We are not going to care, for the most part in this course, where the initial point is. We, in fact, are basically going to move them so many times so that the initial point is simply at 0. And vectors are going to be equal if when we move both of them to 0, they're one on top of the other. Okay, so basically we're saying that the vectors are equal if they have the same magnitude and the same direction. It doesn't matter if they start what their initial point and terminal point are. They are going to be the same if they have the same magnitude and direction. So let's just look at this plot here where we have a bunch of vectors drawn and ask how many vectors are in this drawing. And the idea is that some of them are not unique. So let us take a look at, for example, this one here and this one here. Those are the same vector. Okay, they are the same length, and they are pointing in the same direction. So it does not matter that one of them is in a different position to another. Similarly, these vectors are the same. This guy is the same as this one and as this one. Those three are all the same. They are in different positions, I agree, but they have the same magnitude, that is the length of them is the same, and they are pointing in the same direction. So that is a distinct one there. And then there's a one guy that doesn't have a copy of himself there, that guy there. So there are three vectors here in this drawing. Okay. The zero vector. If A is equal to B, and by that it means if the initial point, that is the initial point, is equal to the terminal point, then the magnitude of the vector, the length of it, is 0, and the direction doesn't matter. We just call that the zero vector, and we denote it by the bold 0. So of course, when I need the zero vector, I'm going to write it like that. That is going to be the zero vector. Okay, so this is, at this point, you want to be able to understand what's the difference between a scalar and a vector, and that understand that a vector has magnitude and direction, and that basically we're not worrying about where they're oriented in the plane. All right, next thing we can do, we can add vectors. Okay, and what does it mean to add two vectors? Well, here's two vectors here. I will call this upper vector here a v, and this lower vector here a w. Okay, so those two vectors. When we wish to add them, what we do is we translate or we move vector W up here. It's the same vector. We put it here like that. Okay, so that is, so we imagine in fact what we do is we walk along V, and then we walk along, we get to this point right here by walking from the origin to the end of V, and then we're going to walk along W, but in order to walk along W, it needs to be moved up, and the initial point of W has to be put on the terminal point of V. And then we draw the resultant vector, and that is going to be, I'll draw it in red. This is a straight line, folks. It's a little hard to draw a straight line sometimes. So that resultant vector, that is V plus W. Okay, so sometimes we when we draw those three, we call that the triangle law, and then sometimes, in fact, you could of course draw in V over here like that. It doesn't matter if you go along V first, go along W first and then go along V, you end up in the same place. So sometimes you can see now I've drawn a parallelogram with the sum of those two things as that diagonal there. So sometimes it's called the parallelogram rule of addition, or the triangle rule of addition. And you can see from the drawing, in fact, that there's an important thing to be noticed, and that is that V plus W is equal to W plus V. So the addition is, vector addition is commutative. Sometimes we will call, we have a fancy way of talking about this, and that is sometimes we will call this resultant vector here, if we were thinking of going along this path, this way to get there, we would call that the translation of V by W. Okay, what does that mean? That means I take the terminal point of V and I move it along W. If I'm thinking of going this way along V and then up that way, I'm thinking of taking the terminal point of V and moving, the terminal point of W and moving it along V. So on this side here, I think this, I can think of this as the translation of W by V. Okay, so that's just, again, a lot of notation and vocabulary to describe what we're doing. Okay, what does it mean to have a negative of a vector? It just means that it has the same magnitude, but opposite direction. So this is going to be same magnitude, that's the length, and opposite direction. Okay, so the minus W is down here like that. Okay, so this is, if this is W, this guy here is minus W. Okay, so that is taking a negative. So I think it may be obvious at this point then how you can do subtraction. I mean, we could have W minus V, and we could be thinking of that as W plus minus V. We can first form minus V, and then we can go up and do the addition just like we did above. I'll do an example of that in a second. First, before I do that, I'm going to do what is called scalar multiplication. So we're going to be very careful. We're going to see coming soon vector multiplication. That's quite different. So now what I'm thinking of doing is taking a single vector and multiplying it by a scalar, a number. Okay, so this is take a vector V. So let's call this vector V. There it is. And then multiply it by a number, a scalar, K. Okay, K is scalar. It has no direction. Okay, let us assume for way of example, we have k equal to 2. Then I would have 2k would be this vector. Sorry, 2v would be this vector here. So v, as you recall, is to there, and then this longer one here, twice as long, is 2v. So it's in the same direction, but it's twice as long. So this is a scaling. Right? It could be half v, 3 times v. It scales it. It shrinks it or stretches it. Okay, we discussed just a little bit above a vector subtraction. Let's just draw an example of that so we can see how it's working. There is, for example, vector w, and here is vector v. There it is. And so if we wish to compute w minus v, so our idea is to see what is w minus v, then what we do is we form the vector minus v, which is the same length and in the opposite direction. So let me try to get that. It looks visibly looking the same length. So this thing here is the same opposite direction of v and the same length. So this is minus v. And then now I will add those together. I will add w plus minus v. And to do that, I put the initial point of v on the terminal point of minus v. So that looks like that. Approximately, let's get it the right length, approximately like that. So this is w. And then I'm going to add those two things together, giving me the answer. That is going to be this guy right here. Okay, so that guy right there is w minus v. Okay, so now we've introduced the idea of a scalar, of a vector, and we know how to add and subtract vectors, and we know how to multiply a vector by a scalar. We did this so far geometrically by we did it by this parallelogram, by drawing a picture and seeing what's going on. We can do this algebraically as well, and we're going to see how to do that right now. So in 2 space, which is 2-dimensional space, which here in my notes here is indicated with this R2, and I sometimes will write with the double bar like this, R2. Okay, that is this means 2-dimensional space. We're given a vector v, there it is, and we wish to represent this thing algebraically. What we do is we move it down so that this initial point here is at the origin. So we're just going to move the vector down here. This is still v. It's an equivalent. It's the same vector because it has the same magnitude and the same direction. And there now it has its initial point at the origin. And then we take a look here at the terminal point. Let me just maybe a little red dot there so we see what I'm doing. So I'm looking here now at that terminal point, and I represent this vector v as the coefficient of that terminal point. So I write it like this: v equals 2, 1. So that 2 is the x-coordinate right here of that red dot, and then the 1 is the y-coordinate of the red dot. The other thing I could do is I could label this, for example, point A and point B, like that. And I would notice then that point A is 2, 2, and point B is 4, 3. And then I would be able to compute from that without having to do the translation that the vector v is the x-coordinate of the terminal point minus the x-coordinate of the initial point. And that is the x-coordinate. And then I look at the y-coordinate of the terminal point minus the y-coordinate of the initial point. And I get this here, 2, 1. Same thing, okay? 2, 1. Okay, now you may ask a good question, and that is, how do I know if you're talking about a point or talking about a vector? Because when I write a point, it looks like that. And when I write a vector, it looks like that. And the answer is you don't. This is by context. If it's like this, and I'm talking about a vector, this indicates a vector. If I am talking about a point in the XY plane, and I say a point at some point, and I use this notation, then I will be talking about a point. So it's by context. So that is the two-dimensional situation. Now, one thing that's, I think, kind of cool about the linear algebra is we can soon just sort of, we can go into any number of dimensions that we like at sort of any time. And we are now going to say in n space, then the vector that we have is an ordered n tuple, which just basically means here that we've got a vector, and if it's n-dimensional, if it's in n space, then we have n numbers here. Okay, so for example, in R3, we could have a vector. Let me just call it V1. That's a vector, and we could have it would have 3 numbers there, and we could be thinking of those as for example, x, y, and z coordinates. And then we would have a vector from the origin to in 3 dimensions to that x, y, z coordinate. Similarly, we could be thinking in R4, and we could have some other vector. Let me just call it V2. That could have some coordinates like that. And so we now have a vector in 4-dimensional space, and it's pointing from the origin to that point. I mean, I find this difficult to visualize, but there's no, I mean, when we're doing things like this abstractly, there's no reason to not allow this, except that we may have visualization problems. And it's this idea, though, this is not completely sort of arbitrarily with no application, shall we say. But so, for example, oftentimes we would have in R3, we would be considering this to be describe, we could think of this at least as describing a point. Let's not put it that way. Describe a line from the origin to a point in 3D space. Now we could consider this to be a similar idea in 4D space, or we can consider this to be represent three numbers being a point in space, and the fourth being time. Let's see, the fourth number, 3 numbers being a point in space, and the fourth number being time, in which case it would be unlikely to be negative. Okay, so we would then have the idea of this 4-tuple indicating a space-time coordinate. This is the Einstein idea. Okay, so now moving along, we want to say, what does it mean when 2 vectors, what does it mean for them to be equal? So equality of vectors, when are 2 vectors equal? And the answer to that is when all of their components are equal. Okay, so I mean, if I have vector u equal to 1, 2, 3, and I have vector v equal to 1, 2, 3, then u is equal to v. If we had some other vector w equals to 1, 2, 4, then u is not equal to w. Okay, they have to all be the same. The 0 vector, we already sort of brought this up, the 0 vector. So in R2, the 0 vector is 0, 0. In R3, the 0 vector is 0, 0, 0, and so on. So in Rn, the 0 vector has n of these things. Okay, and there's n of these. So this is the origin, okay, in Rn. Okay. We talked about the geometric way of adding. There's that picture of the triangle method. We've got u and v, and then we go from the initial point on u to the terminal point on v to get u plus v. However, we can do this algebraically. We can imagine that we have u given to us as u1 and u2, the two components of u, and then we would similarly could have v given to us in this manner, two numbers, v1, v2, and then when we wish to add them, u plus v, we simply can add the components. So this would then be u1 plus v1, and then the y component would be u2 plus v2. Okay, so it's very simple when you have the vectors represented algebraically with their components, and you wish to add, then you simply add the individual components. Similarly, if you wanted to take minus v, you would simply take the minus of each component, like that. Okay. Let us take a example of this. This is v, which is I'm giving you just picking some numbers here. So here's a three-dimensional vector with components x component 1, y component 5, and z component 7. And I'll just pick another vector somewhat randomly, 2, 9, and 4, shall we say. And then, so clearly we are in R3. And I am going to add those two vectors. So I'm saying, what is u plus v? And so what I do is I add the components. So I add the x components here, then first component, then I add the second component, often called the y component, and then I add the third component. And that is 3, 14, and 11. Okay, so we noticed before geometrically, but now of course you could add the components the other way around, and you would see that u plus v is equal to v plus u. It's commutative. I'm stressing this point actually because we're going to see that when we get to matrix multiplication, it is not commutative. And depending on your sort of experience with mathematics so far, you have most likely always run into things where the operations, the arithmetic operations, are commutative, and that will not be the case for the multiplication of matrices. That's sort of a big moment actually. There was a lot of interesting work done to work that all out. Okay, here we've got u minus v. So that is going to look like this. u1, the first component of u, minus the first component of v, and then u2 minus v2, and then u3 minus v3. And I could do that with the numbers that we are using. Let's see, u minus v, so that would be 2 minus 1, and then 9 minus 5, and then 4 minus 7, and then I would write that like this, 1, 4 minus 3. Okay, so that is u minus v. I could also think of this, if I wanted, as u plus minus v, and then I could form minus v in this manner, minus 1, minus 5, and minus 7, and then I could simply add. Either way is fine. Okay, so that is addition and subtraction done algebraically, not done geometrically like we did just earlier. All right, now I'm going to take a vector, u, and I'm going to multiply it by a scalar. You notice that this is in the non-bolded font. That is a scalar. So let us just take an example. I don't know, let c be equal to 5, a scalar, and u be some vector, 2, 9, 4, just like we had before. Okay, then when I multiply the vector u by the scalar c, I will multiply each one of the components. So it will be 2 times 5, giving me 10, 9 times 5, and 4 times 5. Okay, so I simply, when I want to multiply a vector by a scalar, I multiply each one of the components by that scalar. So in the general term, in the general view of this, it looks like this: c times u1, c times u2, c, and however many numbers are in there. Okay, I go through them all. All right, moving along here. There are some properties of vectors that are presented in your textbook in theorems 1.1.5 and 1.1.6. I believe a couple of them are proved, and then some of the other ones, there's exercises for you to try to prove them. I would actually encourage you to do that. If you prove the things to yourself, you do get quite a bit of clarity and your understanding goes well up. Okay, so here is what we've said actually twice before. Addition is commutative. Here's another one here. Addition, this is addition is associative. Here we have the zero vector is the additive identity. That means if we add the zero vector to any vector, it will not do anything. Here we have two properties, this one here and this one here, that is scalar multiplication is distributive. Okay, and then here we have that scalar multiplication is associative. I don't think any of these properties are particularly surprising, but indeed we need to state them and make sure that that we have them. Similarly, here we have one is the scalar one here for scalar multiplication. One is the multiplicative identity. So if I multiply a vector u by the scalar one, nothing happens. Here we have that if we multiply by -1, we simply get the minus of the vector. If we multiply a vector by 0, we get the 0 vector. And if we multiply a scalar k by the 0 vector, we end up with the 0 vector. Okay, so properties. We will use these as we're going through and doing problems. Okay, how do we tell if two vectors are parallel? So let's just start this with an example. Here's a vector, u is equal to 2, 3, 4, and v is a vector, and it is equal to 4, 6, 8. So I'm telling you that if I drew these two lines, that they would be parallel to one another. And how do I know that? I know that they are parallel, and because v is equal to 2 times u. That's what this is telling us. So we use the word parallel and we use the word collinear interchangeably. So you may hear either one of those. So if I can find this value k such that u equals kv or v equals ku for some value of k, that's a real number, then I can tell you immediately that these vectors are parallel. Parallel. Okay. All right, here comes an important one. This is really important. I want you to Important. Here, let me note this. Important. So this is gonna come up in a variety of different forms over and over and over again. So consider this carefully right now, and then you may find that next lecture we're talking about something else. It comes up again. You may want to consider this idea again, the idea of a linear combination and what that exactly means. So here it is. Here's the definition. A vector W is a linear combination of some other vectors if it can be expressed in the form W is equal to a weighted sum of all of the other vectors. So I get given all these vectors v1, v2, vk. Then I get given some other vector w. If I can make w equal to some scalar times v1 plus some other scalar times v2, and I can make w, then I say that w is a linear combination. Okay, let's give an example. v1 equal to 1, 2, 3. v2 equal to 2, 0, 4. Okay, then I'm going to give you a w here. W is equal to -4, 4, -6. And then I could ask the question, is W a linear combination of v1 and v2? So that means, can I do this? W is equal to, well, okay, let me just do it this way. C1 times v1 plus C2 times v2. Is it possible to do that? That would mean, is it possible to take these numbers, -4, 4, -6, and make them equal to C1 times 1, 2, 3 plus C2 times 2, 0, 4. Is that possible? That's my question. Perhaps you can see actually how you can turn this into a system of linear equations and use the tactics that we had from sections 2.1, 2.2, and 2.3. Yeah, so think about that. So that is my question, and I'm going to tell you in this case, yes, the answer is yes, because W is in fact equal to 2 times V1 minus 3 times V2. Let's see if I'm right. So the thing is -4, 4, -6. That's W. Is that equal to 2 times 1, 2, 3 minus 3 times 2, 0, 4? So to check that, I would be wondering, is -4 equal to 2 minus 6? Yes. Okay, and then I would go on to the next one. I would be checking this 4 here then. 4, is that equal to 2 times 2 minus 3? Yes. And then I would do the last one, checking this term right here. Is -6 equal to 2 times 3 minus 3 times 4? And that is equal to -6. Yes, it is. Okay, so it is true that W is a linear combination of V1 and V2 because I can express it in this form and I can find these numbers there, 2 and 3. Okay, so perhaps think about seeing this here. Would this allow you to find out what C1 and C2 are? How do I find that 2 and the -3? That is something we're going to be doing frequently. Okay, finally, to wrap up this discussion, we're going to formally introduce what is a matrix. We've clearly seen these already, but a matrix is simply a rectangular array of numbers. Okay, we express the number of rows first and then the number of columns. When we say the size is m by n, that means it has m rows and n columns. So here's a 3 by 4 matrix. It has 3 rows. That's these guys here, 1, 2, 3, 3 rows, and it has 4 columns. 4 columns. Okay, so by convention, we're saying this is a 3 by 4 matrix. You have to make sure that you don't confuse which one is the rows and which one is the column. So the first one is the row, and then the second one is the column. Okay, we can think of a vector as a special type of matrix. Okay, so a matrix with one row equals a row vector. How about that? So for example, here is a row vector. It's a 1 by, in this case, a 1 by 4 matrix. Okay, how about a matrix with 1 column? Okay, that's going to be, guess what? A column vector. And let's give an example of that. We write it as a column because it's a column vector. 1, minus 2, minus 3. So this is a, this example here is has 3 rows, has 1 column. It's a 3 by 1 matrix, and it is also called a column vector. Okay, let's take a look at this original matrix here, M. So let's look at matrix M. I have 2 ways of thinking about this. 3 row vectors, 3 row vectors in R4, right? I have 3 of these 3 rows. Let me just add confusion. 3 rows, that's this statement right here, 3 rows, and each row has 4 entries. So that would be a 4-dimensional object. Or I could think of it in this way, 4 column vectors in R3. Okay, so that's a possibility, a way of thinking of a vector, a row vector, a column vector, and we've also seen the comma delimited form. So we had this, we have earlier just been using this, what we would call the comma delimited form. And that we've seen like this. In this case, we didn't really have the notation of it being a column or a row. We just said there's our vector. Okay, but we might be thinking of it as a row vector or a column vector if we're thinking of it as 1 row or 1 column, a special type of matrix. Okay, we saw in the last lecture that we can capture all of the information in a system of linear equations in a matrix, in a particular type of matrix, in fact, which is an augmented matrix. I'm going to show you here how we can capture something completely different in a matrix. So here's what we're going to do is capture the incident matrix of a graph. So this thing here, this little thing that looks like a house, this is called a graph, and it has vertices. That are these guys here. That is a vertex, 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 and vertex. So these things are called vertices. And then between vertices, there may or may not be a connection. So between vertex 1 and 5, there's a connection, connection B, and that's called an edge. Okay, between 1 and 4, there is no edge. There's no connection. So I mean, imagine yourself driving around in a car. You could imagine 1, 2, 3, 4, and 5 being the cities. And in order to go from city 1 to city 3, you could potentially go like this, going down at this one and go down here. Or perhaps you could go down here and then go down here and go down here. You know, this kind of idea, right? Or you could go down here and go down here and go over here. So you can move between the vertices using the edges, but you're not allowed to go like this. That's not allowed. There's no road. Okay, so that's the idea. So we have here the edges A, B, C, D, E, and F. Okay, and we can capture this graph, we can capture also in a matrix. And how I'm going to do that is, well, first of all, here, I notice that there is 5 vertices, and I notice that there is 6 edges. Okay, so I'm going to have here 5 rows, and here I'm going to have 6 columns. Okay, and in this matrix, I'm going to say, let me just call this matrix A so I can talk about it. This is matrix A, and what I'm going to do is say the entry Aij is going to be equal to 1. Now, what do I mean here, Aij? What I mean is, look at matrix A, look at the ith row, and then look at the jth column. Okay, so for example, A23 would be is equal to the entry on row 2, column 3. Okay, I'm going to make that a 1 if VI and EJ are adjacent. And otherwise, I'm going to make it a 0. This is how, but this is going to be my rule for taking this graph and capturing the information about this graph into a matrix. I'm going to call that matrix A. So here, I'm going to put a 1. Why? Because these things, because edge A is attached to vertex 1. I'm also going to put a 1 here for the same reason, because edge B is attached to vertex 1. Notice that edge C, D, E, and F do not go to vertex 1. So I put zeros at those locations. So all these guys are zeros. Again, I just keep going. I go through this like that. I look, okay, let us look at vertex 2. Edge A is there, attached to vertex 2. Edge C is attached, and edge F is attached. Then I put zeros in the rest. I go to vertex 3 down here, and I see that E and F are attached. And then I go and fill in zeros everywhere else. Okay, and then I do it for 4, and which ones are attached to 4, D and E. And then I go to vertex 5, and I see B, C, and D, B, C, D. Okay, then I'm done. All right, so what you should be able to do now is take this adjacent incident matrix and draw this. Try it out. Try to, I mean, you know what it has to look like, but take A and then start with vertex 1 like that. Say, okay, I've got a 1 there. What do I have it to? Oh, A and B head out from it like that, A and B, and then keep going like this, and see if you can regenerate the drawing. You should be able to. Okay, so this is very different from our system of linear equations. I have here a 5 by 6 matrix that represents this graph above in a particular manner. Now, consider if I took that same matrix. Here, I'm going to take the same matrix. I'm just going to write it out here. Write it like this, actually. 1, 2, 3, 4 zeros, and then 1, 0, 1. I'm just copying matrix A again here. Let's see. There it is. And just given this matrix and no context, it could be a incident matrix of the graph. Or imagine if I said, oh, maybe it's an augmented matrix for a system of linear equations. Then this very same matrix, the very same numbers in the very same order would mean this, right? x1 plus x2 equals 0. x1 plus x3 equals 1. So this is coming from row 1. This is coming from row 2. I'm thinking of it now as an augmented matrix for a system of linear equations. x5 is equal to 1. X5 plus x6 is equal to 0. And x2 plus x3 plus x4 is equal to 0. So the meaning of A it is dependent upon how we generated it in some sense. So the context is important. And then further, we can now consider this matrix A, this numbers, and we can actually do operations on this thing. And we can define things about it like that, independent of the context of which it arose. So it gets a little bit more abstract, but oftentimes the matrices are coming to us from somewhere, and then we're going to operate on them depending on what we're trying to do and what we're trying to figure out. But the same matrix can come from two very different looking applications. Okay, that is section 1.1. I will be back with section 1.2. Thank you very much. Bye.